Hello. First, thanks for staying. This is maybe too much for the last lecture, but yeah, let's try. So, in a nutshell, we will talk about Nix package manager and how we can use it to use it as the development and deployment tool. So my name is Luka. I'm mostly into DevOps orchestration work. I'm also doing development on embedded hardware. Yeah, and my daily job is using various tools to deploy apps and stacks. So Nix was one of the experiments which gave me pretty nice tool how to compose my software in a way I wanted, and also define some guarantees which are expected in deploys where we want to ensure that all our deploys are reproducible. So when we do a redeploy, we can guarantee, or our system can guarantee, that this deploy will be the same as one we did yesterday. So Nix is language and the package manager. So language, this is a specialized language which we use to define the package structure, or we can define it to define our complete stack. So we can see it as DSL, like specialized language for this use case. It is also a package manager, like Debian has apt, Red Hat Yum. So it behaves like normal package manager. It also has a central database, which is called Nix packages. So you can use it to install, find the packages you need. So it works like traditional package manager, but it has some differences. We will see that in interactive part. So you can see Nix as DSL. So DSL, which will hide all the let's say ugly part of your deploy. So you will compose how your stack should look like, and also define it in a way that when you write the final definition, you won't see the ugly part. Let's say when you don't want to see how the apps are built. You just want to get the set of the apps you need. So Nix hides this from us. We can also compare Nix with Docker. So I don't know if how many of you used Docker? And no, oh great. So typical Docker image. We have some base image, which should be here, and we add something we need, and we create our own custom layer. Then we add some code, it's a second layer, and we run code. Okay. In Nix, it's a little bit different. It's not it's a graph. So basically, all our packages or our definitions have dependencies around them. And the interesting part is that all those dependencies are determined. So we can point to that derivation or that package by using the hash of the derivation. So if we change something in this graph, all the dependencies will be rebuilt. So if we change readline, then ncurses will be rebuilt from scratch because dependency change. But top level dependency won't, because it's not dependent on readline. Also, if we do it with the bash, we will get everything which is dependent on bash rebuilt. So let's see this Nix in action, and hopefully you will get some feeling how is it used. Okay, just a second. Should be better. Okay, so first we'll start with the installation of the Nix package manager. So you can install this package manager side by side your existing package manager if you are using Linux distribution, or you can even install it on your Mac. It will work normally on your Mac machine. So this example will show the basic installation in single user mode, where we create. Only thing we need to create for Nix is /Nix directory. In this directory, he will install all the dependencies, packages, everything. Even he will install Nix package manager in this store. So yeah, we will download something from some shell script, execute it on our machine, and it will set up everything for us. After that, we want to update the channel list. So this Nix channel update is the equivalent to apt-get update in Debian or yum update. It will download the latest version of the Nix packages. Thing I forgot to mention is that Nix is source-based package manager. So in theory, everything should be built from scratch. So it will just define how things should be built. And yeah, this is pretty bad. It's like if you are used to Gen 2 usually builds, and this takes time. Nix also provides binary caches. So there are machines which constantly are creating binary caches, so you don't have to build everything from scratch. So we will start by installing Python, some specific Python version, to see what will happen. So we will get binary caches found on main cache repository. So this command generated a list of tree or dependency which are needed to have Python working on our system. So we can see that this top-level Python derivation generated dependencies which can be determined by this hash. So we can easily check if this cache is available. If this cache is not available in main cache repository, Nix will automatically start building, and also it will fetch all the build dependencies for this missing package. So we can now when we enter to this Python 3 environment, we will be, let's say you are entered in Docker container. Now you are entered into the Nix shell. In this Nix shell, you have Python 3.5 available. So you can have ad hoc environments where you can experiment, or you can have specific version pinned. And as you can see here in Nix shell, we got the version we wanted. We defined 3.5, and on the system, so we exited this Nix shell and came back to a system. So the Python on the system is completely different. So we can also install some dependencies. So we will try with Django, but the problem with Django is that it's not available in the caches. So it will be automatically built from scratch, and also all the Django dependencies which are not in caches. So yeah, we will get environment with Django, and the Python path will be pretty big. Yeah. So so we will get the Python packages and all the Django and all the dependencies of the Django available in our environment. Yeah, we can find almost anything. All the major languages and packages in the repository is pretty big. And yeah, here's a Node.js example. So we can also examine the path of the Nix shell. It will be overridden by all the dependencies. And specific languages will bring their specific environment variables and dependencies. We can also install not only enter to shell or some specialized environment, we can install stuff globally. We can, let's say we will install this bat command, which will be located in our local profile. So when we bootstrapped the Nix, it created our local profile. Local profile is nothing special. It is just a bunch of symlinks. We can see that. Yes. So if we examine this Nix profile, we will see that we have this bat command, which is available in our path, and this bat command points to some binary which is located in Nix store. So basically, we didn't install anything. We just pointed to something which is available in the store. So in Nix, you cannot basically install anything. You can just point to it, and you can construct dependencies which will be available in your environment. So basically, you cannot break the installation. You can always roll back to older version of symlinks, let's say. So let's try to do something more serious. So we'll get some. I created some very simple Node.js app, but it has a lot of problems. We'll try to solve it. Luckily, I recorded this at home, so yeah, it worked. So it is solvable. So this app is using Puppeteer module, which is module. It will open the website in headless Chrome, and we can do whatever we want with that. We can control a browser from the Node.js. In this example, we'll just generate the PDF and return it. And using Express, we can return this PDF to the requester. We will crawl lobsters and see what is new. So this app also has package.json. Like every Node project, it defines two basic dependencies. And we also have a package log file, which is now in recent versions of Node.js. So this package log give us nice things like it has integrity of every dependency we downloaded. So we can use this file to construct the Nix expression, which will define our dependency tree or our environment. So let's try to convert this into a Nix environment. So every major language has a tool like this. So it will take Node.js stuff, and it will generate the Nix expressions, which will define our project, but in very interesting way. So we will see that we can easily generate this, but we will have a lot of problems, because this Puppeteer is using Chrome. And this Chrome is very heavy dependency, and it depends on a lot of stuff. So first time when we will try to generate dependencies or generate the expressions for this package, it won't work because you will see. Because there's a dependency in the build of the Puppeteer. It will try to download the Chrome browser to a local environment. And Nix won't let you to download random stuff from the internet. It will sandbox every build. So you can define what you want to build, but in a build process, there cannot be random downloads, there cannot be random stuff executed because you don't know what you will get. So in this case, we will see that Nix didn't allow Puppeteer module to download Chromium from some Google APIs, because this will break the purity of your build. So we will need to change something. So we will change the code a little bit. Luckily, Puppeteer is coming with Puppeteer core package, which is just a Puppeteer without the Chrome. And we will inject the Chrome through the Nix environment. So we can guarantee that every developer which will use this expression will get the same version of the Chrome, and it will also get the same version of all the packages we defined. So we will do this trivial change. We will add executable path. And this path will be read from the process environment. We need to define where the Chrome is located. Yeah, and change a little bit package JSON. We will now need to regenerate our expressions because we changed how this app is built. So we will run this node to Nix tool, which will regenerate, and now we will need to write something in the Nix language. So let's see how this looks like. So we will write a simple override expression which will inherit the package database. So basically, when we install the Nix, we updated the channels. We run get update. So we get the latest list of the Nix packages on our system. So we will import those packages to this pkgs variable. And we will take default.nix, which is stuff which node2nix generated. So we get the current build of our node project defined in this map. So node packages is basically the current build we got from the node2nix generation. And now we will try to override. Basically, we will inject Chromium into this build system. So we will override this shell which we executed, Nix shell, our project, with additional attributes. So this is very clearly defined in manual how to do this. So basically, you get the old attributes of your derivation. We will just extend the old attributes, list of the build inputs, if there are any in the original derivation, extend it with few additional packages. We also need font configuration for Chromium to work. And we will export two environment variables. Chrome, which we need for where is the Chromium execution located, and the font configuration file. So when we enter to this new Nix environment, it should pick up the Chromium and all the dependencies. So we can see that Chromium is very, very heavy. It will download half of the X files, X subsystem and the renderers and all kinds of stuff. And this time it should pass. So the idea is, the main thing about this example, if we are not using something which will log the dependencies, every developer, if you are running the code on the multiple distributions or not in the same environments, you won't get results. You won't get the same results, because maybe my colleague developer is using a little bit newer version of Ubuntu. I'm using Arch. All the packages are not the same on the distributions. There are random stuff downloaded from the internet. You cannot basically guarantee that final execution of our app will be the same. In this environment, we can easily give every development the same environment, which we define from these expressions. So we can now try to run this app and try to download this PDF and see if it works. It should work. Yeah. So we'll convert it to text so we can display something on a screen. So yeah, it's something. It's not pretty, but yeah, we managed to create a PDF. So I was also talking that we didn't install anything in this tutorial, but we downloaded a lot of stuff. So we downloaded a lot of caches to this Nix store. So yeah, we can try clean this environment. So we can easily clean our system by running Nix garbage collect. So it will collect everything we downloaded and it's not used. So nothing is pointing to these dependencies in a store. We also installed this bat command, if you remember, to our local profile. So if we uninstall the bat from our profile, it will be automatically collect next time when we call the collect garbage. And that's for all from the interactive part. So we can see that everything in this store is defined by the hash, and we can easily modify any dependency we want by overriding stuff in the Nix packages tree. If something changes, everything which is depending on this dependency will be rebuilt from scratch. So we can ensure that we rebuild only what is needed, and that everything is rebuilt which is needed to be rebuilt. So we can also see that in this store, everything is self-contained. So this Python is not using anything from our host system. Everything is located in this store, and we have exact links to and versioned links to dependencies. So we can guarantee that stuff executed anywhere will be run on with the same stuff we defined. But we forgot to define one thing, which is ensure reproducibility. So as I said in this derivation example, we used Nix packages which were located on a local machine. And maybe my fellow developer will have a little bit slightly different version than me, and the build result will be different. So to ensure that the Nix packages are up to date, we can easily fetch or bake the version of them in our expression, so that every time we build this app or derivation, correct version of the Nix packages will be used, so that everything else will be the same. And the final example. So this app was, it will be too much to export it to a Docker container. So I used a simple Redis package. So this derivation will basically create a Docker image. So it's a Docker file, but written in this Nix language. So it will run some shell script. It will create some data directory for the Redis. It will set up permissions. It will export some ports. And in the end, it will run the Redis. It will also export the volumes, so we can remount it to other containers or whatever we want. And this looks like this. We will run this Nix build, and we will get, it will bake the image for us. And we can load it to a Docker, and we will get one very, very old Docker image. Yeah, why this image is so old? Because Nix tries to every files which Nix generates, they are set to epoch 1. So they are set to 1970s, so that when those binary caches are compacted and uploaded and redistributed, so you get the modification time the same on old machines. So that's why this image is so old. And that's it.
Thank you, Luka. Okay, we do have time for quite a few questions if needed, so okay.
Since you did quite a few comparisons with Docker, can you speak about the isolation level of the shell? Like how easy it is to break out of a Nix shell for a process?
Okay, so the Nix shell is purely created for development, so it doesn't have any isolation. So to get the isolation, you can export your app to some standardized Docker container, anything. You can easily create AMI image, so you can run the whole AMI image. Also, if you look the size of your export, you will see it's only 34 megabytes in size. So Nix will only take the stuff which are needed to run your app. So you will get very efficient image, which has minimal dependencies. In this example of Redis, Bash won't be even in it. So we use Bash in this example. We use shell to bootstrap, but the final image won't contain Bash. So it's pretty neat, and you can be very precise what you can put in your image. But the Nix shell, it's purely for developers examining your expressions. So yeah, you can easily create little environments where you can play and experiment. Yes.
More questions? Oh, sure.
Hey, thanks for the talk. I've used like Nix. Like my problem with it is like it's really slow, and I was thinking like this example with Chromium. I only really want to run Chromium because I want to run Puppeteer, but by using Nix, it means I have to pull in all Chromium's dependencies, which are loads, right? So do you have like any suggestions or like tips for making that like a nicer experience?
You mean slow in a way, fetching the dependencies, or didn't get that?
Just like it needs to do like a lot of things, right? So like if you think like the Chromium's like dependency tree is huge.
Yes.
And I don't really need the dependencies. Like I would just like need like Chromium as the binary, right?
Okay.
In that specific case.
So the problem with Chromium binary, you cannot really strip it. So if you want to render a PDF, you will basically need everything which links to this Chromium binary. So in theory, we can examine the Chromium source code, and we can write the expression which will patch the binary, patch the source, and create specialized binary only which will be used as headless Chrome for this Puppeteer usage. So it's it will be possible to remove all the dependencies, and Nix can help us to create very easy patch. So we don't have to fork everything. We can patch it and easily update later. So,
but those were Chrome's runtime dependencies. Those weren't the build dependencies. So those were the things that you need to run Chrome, not just not to build Chrome. Okay.
Yes. It will only fetch the build dependencies when rebuild is needed. Yeah.
More questions? Oh.
Hey, thanks for the talk. So I was wondering, do you have any experience with the new Docker tools layered function that was added quite recently? So it produces, when exporting the image, it produces Docker layers.
Mm-hmm.
That's the first question. And the second question is how easy it is to set up your own cache, for instance, if you're a closed source company or whatever, so you can't have binaries on the main NixOS cache. Thanks.
Okay, so the first question, in the newer Docker versions, those layers can be organized in different way. Not every command will create a new layer. So in Nix, if we do a layering like that, we'll get so much layers because it's pretty big graph. So those dependencies needs to be squashed in some way. So there are tooling in Nix package subsystem which can squash those dependencies. So it will create some nicer dependencies tree, so you don't have to rebuild all the layers again. So basically, you can get that functionality currently from Nix. So it's in upstream, and there's a nice blog post I can show you later. So for binary caches, so in my company in TVBit, we generate our local caches for our software, and we use S3 directly. So we have this S3 is not even protected. So basically, you cannot guess our hashes because you don't know our derivations. So we have an open bucket somewhere on S3 in which we upload the caches. But who is uploading the caches? So if we check the main Nix infrastructure, they have continuous integration built. So it creates the original binary caches we used in this example, and we can use the same CI which they use to build caches for our software, which will be in some separate bucket. That's how we do it. There's also a CacheNix project which provides also pretty nice tooling how to create binary caches much more easier than setting these Hydra continuous integrations from scratch. So there are many options. There's even managed CI for Nix, which will run your expressions on the GitHub, create the binary caches. You can use NixOps to deploy your stuff. So there's a lot of stuff around the Nix package manager, but I wanted to concentrate only on Nix package manager, not about the ecosystem. You can easily find examples.
Any more questions? If not, thank you, Luka. And we're done for the day. I'll see you tomorrow. Thanks for coming.